In this video and in the coming two videos, I will speak about how to calculate in a simple way the correct sample size. Let us start with this video. The Slovin's formula. The Slovin's formula is widely used in research, especially where sample size is crucial for accurate and adequate representation of the population. Although the common name is Slovin's formula, but this name Slovin is not known from where it came. And in the literature it was not clear from where it came. This formula has been invented by Taro Yemeni. Taro Yemeni is a Japanese statistician. But anyhow, the common name went on just like that Slovin's formula. But if you write Taro Yemeni formula, it is 100% correct as well. It allows the researchers to calculate the sample size based on the population size, based on a known population size. The most important thing is that the population size should be known. And we can get the population size when we go to the medical record and ask how many patients were admitted last year in 12 months or in 6 months about any specific disease, or if you go to the laboratory to the histopathology, how many cases have you received the tissues for histopathology for tumors, any tumor, breast tumor, colorectal tumor, gastric tumor, whatever, any type of tumor. They can tell you the total number in that hospital and they have had in complete 1 year or in 6 months. Based on this figure, you can calculate a correct and reliable sample size with a fixed margin of error of 5%. When we say 5% error means it is with a confident level of 95% that this is the correct sample size. The margin of error indicates how much the sample size differ from the true population. When we say it is 5%, means the error we are aiming at is not more than 5%. And we are aiming at a confident level of 95% that our calculation will be correct. I think this point is clear now. The Slovin formula is useful when the population is homogeneous, when the cases are similar to each other. For example, all cases are appendicitis, all cases are road traffic accidents, or all cases are war injuries, or all cases are related to a specific cancer or a specific disease like laparoscopy or for example, open cholecystectomy or laparotomies. They should be homogeneous. The heterogeneous population should be set into strata, and in each stratum different calculation or a specific calculation can be done to reach a sample size. So it doesn't work for inhomogeneous population. It is only for homogeneous similar cases. And it is designed for a finite population, for a limited number of population. the formula, the Slovin formula, or the Taro-Yemeni formula is designed for fixed, and that is finite population, not for infinite population, not for a very big, very huge, endless, in thousands or in millions. No, it is just for a specific number of population. This is important. Now, the Slovene formula, if a population with a specific characteristics, let us say appendicitis, is known, how many cases were admitted in 1 year or in 6 months, we use the Slovene formula or the Taro-Yemeni formula, it is the same, to calculate the sample size, which is denoted by a small n. The total population, that is admission in 1 year, the total admission in 1 year are denoted by a capital N, that is the total population. And the sample size we are going to select and study is denoted by a small n. And the margin of the acceptable margin of error is denoted by E, by the letter E. And it is taken all the time as 5%. And when we calculate the 5%, we write it as 0.05. Anyhow, it is 5%. We will come to that soon. Slovene formula is useful when the population, as I said, is homogeneous. All have one diagnosis. It is designed for finite, for limited number of population. These facts are crucial, are important. And as I said, the margin of error indicates how much the sample size differ from the true population. This is a formula, the Slovene formula. The sample size denoted by a small n is equal to the specific population in 1 year or in 6 months, denoted by capital N, divided by 1 plus the same number of population multiplied by the margin of error squared. That is, n is equal to capital N divided by 1 plus capital N multiplied by E squared. Let us speak by examples, it will be more clear. Hospital records, for example, let us take an example. If the hospital record shows 700 diabetic septic feet or diabetic septic ulcers in 1 year time, in 12 months, what is the adequate and representative sample size for a study on the outcomes of a diabetic septic foot in 1 year? So the number in 1 year is 700, and we are going to calculate also for the same period. We have to use the same period. Now we write the formula, which is n equal capital N divided by 1 plus capital N multiplied by square E. N, as we said, 700 diabetic septic foot patients or septic ulcers. And E is the acceptable margin of error, and we always take it as 5% at confidence level of 95%. So the formula, if we replace the figures, will be n, the sample size is equal to 700 divided by 1 plus 700 multiplied by 5% to square. But do we write 5% to square? No. We write 0.05 instead of 5%. Why? Let me explain this. 1 is usually equal to 100%, right? 1 is equivalent to 100%. Half this one, it is 0.5. It is equivalent to 50%. Half, which is 0.5, equivalent to 50%. 0.05 is equal to 5%. Now clear, isn't it? We move on. So if we continue the formula, the sample size will be equal to 700 divided by 1 plus 700 multiplied by 0.05 multiplied by 0.05. That is 0.05 square. That is a 5% square. And we know 0.05, 2 decimals multiplied by 0.05, 2 decimals will end up with 4 decimals, will end up with 0.0025. Now we are going to multiply 700 by 0.005 and we add 1, and then after that we divide 700 by this sum. And let us move forward. This is a Slovin formula. N is equal to the population size divided by 1 plus n, the population size, multiplied by the margin of error squared. And as we said in our example, the sample size is 700 diabetic foot ulcers in 1 year, divided by 1 plus 700 multiplied by 0.0025. That is a 5% square. Okay, we move forward. Now, 700 multiplied by 0.0025 is equal to 1.7500. So it is equal to 1.75. If we add 1, it will be 2.75. Now the equation will be n is equal to 700 divided by 2.75. Is this clear? If we divide 700 by 2.75, the result will be 254.5. There is no fraction of a patient or fraction of a file. We round it up to a complete figure. So n will be equal to 255. The sample size will be 255. Is this clear? Instead of studying 700 cases, we are going to study 255. But usually we find that some files are deficient in data, and some files might be torn or might be lost, and if we are dealing with patients, some patients might refuse to continue, and they have the right to withdraw from the research. So, or they are not willing to give all the answers. So for these attritions, for these dropouts, or these losses in the amount of information we are going to get, we have to add to the number of files or to the number of patients, we have to add to the sample size between 10 to 20% according to the status of our medical record. In war, probably we need to add 20% because files will get lost and the investigations will not be there, and a lot of data will be missed, not written. So we can add 20%. But if everything is kept neat and decent and carefully kept, then we can add just 10% to replace the attritions, to replace the losses of data in some files. Now we have to calculate 10% and add it to 255 and see what will be the final correct sample size. If the data is well organized, we add 10%. But if the data is messy or likely to be incomplete, we can add 20%. Always add extra number, add extra percentage, so that you should not finish with insufficient data and hence invalid results. Now this point is clear. Okay, compensation for attritions, for the losses. Now we'll see if we compensate 10%. The number n, it was 255. If we add 10%, we are going to add 25.5. And the total will be 280.5. There is no 0.5 file, no 0.5 patient. We have to round it up to a complete figure. And the total sample size will be approximately, you see, this is not two parallel lines, a little bit wavy lines, approximately it is 281. We study 281 instead of studying 700. So we are going to gain energy, we are going to gain time, we are going to gain money, we are not going to lose energy and time and studying 700, we study only 281. Not only that, to make it more easy, if you are studying something about diabetic septic foot, we can fractionate our study into a prospective limb and a retrospective limb, and then to compare between the outcomes of both. If there is difference in the outcomes, means there is negative impact of war on these patients. If the outcomes or in the prospective patients is poorer than or is worse than that in the retrospective, means before war we were handling patients perfectly and the results were very good, and war has affected those currently under treatment and the result is not that good. And the fractionation into prospective and retrospective could be with a ratio of 1 to 1. 1 to 1. So 291 can be divided into 2 for each limb. Or the fractionation can be 1 to 2. Can be 1 to 2. So we can study prospective patients, only 93 patients. Only 93 patients. And we study the files of a retrospective study of 188. So this is a simple study, isn't it? This is quite a simple study. Now let us take another example, and things will become more clear with examples. If the number of open cholecystectomies is 120 over 6 months, now we are taking a different period. 120 open cholecystectomy over 6 months. What is the adequate and representative sample size for a study on the outcomes of open cholecystectomy over 6 months? Same period, with a margin of error of 5%. That is confidence interval of 95%. Our sample size will be correct and our calculation will be correct, and hence it will be generalizable. Now we introduce the Slovin or the Taro-Yamin formula. It is N equal the population size, which is 120 open cholecystectomies, divided by 1 plus the population, which is 120 cholecystectomies over 6 months, multiplied by the margin of error squared, E squared. So we know capital N, the population is 120, and we know the margin of error is 5%, and we know we write the 5% 0.05. 0.05 is 5%, because we said 1 is equivalent to 100%. Repeat again. Half this one is 50%. Half this one means 0.5. 1/2 is 0.5. It is 50%. Then 0.05 is only 5%. Okay? And let us continue with the calculation. So the sample size n will be equal to 120 divided by 1 plus 120 multiplied by e square, which is 0.05 multiplied by 0.05, which is 4 decimals, 0.0025. We have to multiply it by 120, and then we add 1. And then we divide 120 by the result we are getting from this calculation. This is the same Slovin's formula, or Taro Yemeni formula, the same. The population 120 divided by 1 plus the population 120 multiplied by e square, which is 0.0025. Now 0.25 multiplied by 120 will be equal to 0.3000. It is 0.3. When we add 1, it will be 1.3. And when we divide 120 by 1.3, the result will be 92.3. Is there any 0.3 patients or 0.3 file? We round it up to a complete figure, which is 93 files or 93 patients. Now it's clear. What is missing? The missing data. If you are studying files, probably some files are missing. If you are studying patients, probably some patients will discontinue or will refuse giving information, will not like to contribute or participate in our study. For this attrition, for these losses of data, we can add, we said, if our system is perfect, we can add 10%. And if it is not, if it is messy and not in good order, then we can add 20%. Let us add 10% to 93. To 93, when we add 10%, it is 9.3. And let us continue. When we add 9.3, so the sample size will be 102.3. There is nothing called 0.35 or 0.3 patients, so we round it up again, and the sample size will be 103, 103 patients or 103 files. It's clear now, isn't it? Now let us discuss another thing. To finish up, we are just about to finish. We said the total population is 120. And now we calculate it perfectly well. The sample size is approximately equal to 103. Why not to study the whole 120? What is the problem? Why not to study it? If we study only 130, it is perfect, it is well, no problem at all. It will give us a good result, generalizable result, valid result. But the difference with the total population is so small. Now, we said if we are using these 103 patients, how are we going to start? We start first by randomization. We are not going to take the first file, probably the third file or the seventh file, and then we continue. We take the first randomly, and then we continue every second or every third like this till we complete the number 103. So we have some sort of randomization in collecting these 103 cases or 103 files. There is some randomization. If we take the 120, the whole population, of open cholecystectomy, 120 over 6 months, then we are not going to miss anything. We are not going to do any randomization. We will not have any randomization bias. We will not say that randomization might select for us some missing files or some files with missing data or something like this. No. We are studying the whole thing. So when the difference is small between the sample size and the total population size, it is better to take the census, that is the complete population. It is better to take 120. However, if you studied 103, it is also correct. Understand? See the difference between this and the first example. That the difference in the first example was very big. We are studying 200 plus and the total population was 700. Very big difference. So we are going to study our sample size. We calculate it. But here the difference is minimum. So we better take the whole population. We take the whole census. But if we study only 103, we are also correct and our result is also applicable and generalizable. This is the same data. We calculated the same thing. When we multiplied 5% square, which is 0.05, multiplied by 0.05, which is equivalent to 0.005, which is equivalent to 0.0025. We multiplied by the capital N, the total population, which is the total number of cholecystectomies in 6 months, 120. The result will be 3. And we add 1, it will be, the result will be 0.3. 0.3. When we add 1, it will be 1.3. And when we divide the population size, which is 120, by 1.3, the result will be 92.3. We round it up to 3. And when we add the 10%, it will become 103. And we said the difference is minimum, so we continue with the whole sample. And we said if the difference with the census is small, we use census to eliminate the bias of randomization. Now clear. The indication of Slovin formula, or better to say the Taro Yemeni formula, the Japanese statistician who invented this formula, the indication is that the size of the population should be known, must be known, and the margin of error is fixed. It is 5%. Confidence interval 95%. The contraindication is that if the population, the general population with similar characteristics, that is appendicitis, cholecystitis, one type of tumor like that, if the number is very small population, better to consider the census, the whole population. And if the population is heterogeneous, we need to classify the population which is heterogeneous into strata. And from each stratum, we calculate the sample size. So we will not use the Slovin's formula. So 2 contraindications: very small population size, we use the census, and heterogeneous, we do not use Slovin. Otherwise, we use Slovin. And to this point, I come to the end. I hope it is easy and clear, and the formula is very easy. The sample size, small n, is equal to the population, which is capital N, divided by 1 plus the total population, capital N, multiplied by E square, which is a margin of error, which is fixed 5% square. Hope this is clear now. And in the coming 2 videos, I will speak about another 2 formulas more easier than this one. See you in the next video.